Hello. In this video, we are going to start off with the resolution of vectors, where we are going to discuss how a given vector can be resolved into components. Now, what do you mean by the term resolution or resolving a vector? In case of a given vector, as you know, we have studied that we can obtain a resultant which is just the addition of two or more given vectors. Now, here these two things have been given, that is, the A vector and the B vector are given, and from that we are obtaining the resultant. But what about the other way round? The other way round is obviously obtaining A and B is obtaining A and B vector from the resultant R vector. That is when we say we are resolving R into two separate vectors A and B such that R is the resultant of A and B. Now, in this case, we have two vectors. Now, we can resolve a given vector into many other vectors possible. The simplest approach, now diagrammatically, obviously, it is like this, that we have an R vector, and we are resolving it into two components where we are having two non-parallel vectors, obviously non-parallel vectors in the form like this. Suppose this is the B vector, uh, and this one is the A vector. So this is the B vector and this was the A vector, and from that you had this resultant, which we obviously used, where we have obviously used the polygon law. Now we have sorry, the polygon law, I'm saying it's a parallelogram law. So we have in fact obtained A and B out of R. If we are going the other way around, then we are getting two non-parallel vectors A and B, whose sum, whose vector sum, not just the sum, whose vector sum is R. And then we can say that A and B are two components of R. The simplest form are the rectangular components. As the name suggests, the rectangle with having different lengths of the sides but perpendicular to one another. Now, if suppose we have a vector, a given vector, let us suppose say it is A. So this is a vector A, right? And we are considering the coordinate system with the x-axis and the y-axis. Obviously, they are normal to one another. Now, in this case, these two axes being perpendicular to one another, right? And if suppose I was to obtain the projection of A along the x-axis, and let us suppose that the A vector is making an angle theta with respect to the x-axis. So how do I obtain the component or the projection? So I just drop a perpendicular from A on the x-axis. So this actually is the projection. Let me write that as AX. So AX is the projection of the A vector along the x direction. While if I drop a perpendicular like this on the y-axis from the tail of the vector, then what I have is the projection of A on the y-axis. Let me take it as AY being the projection of A vector on the y-axis. Now, as we see that AX is a new vector which is directed along the x direction, and we know about unit vectors along the x, y and z direction. The unit vector along the x direction is I cap. Now unit vector has been magnified, or we can say has been multiplied with a value or magnitude of AX. So we have AX to be the value or the magnitude along the along the x direction. And we also have another vector AY which is having the magnitude AY along the y direction. So the unit vector in that case is J cap. Now what if we add up these two vectors? Now adding up these two vectors is the approach to obtain the vector A, because as you can see from the figure over there that AY and AX have a resultant. AY and AX have a resultant which is given by A in this case. Let's check it if it's actually giving A in this case. Obviously, as you can see that these are rectangular components, then we can have A square plus B square. B square, instead of B we have AY, instead of A we have AX. That is the way of vector addition, the way to find the magnitude. And AX squared plus AY squared plus 2 times of AX multiplied with AY multiplied with the cosine of the angle between them. Now the cosine of the angle between them in this case is 90 degrees. As you can see, cos 90 goes to 0. So all we have left is AX squared plus AY squared, while the rest of the term goes to 0. So this is what we have when we add up these two projections of A. As of now we can take them as projections of A. Now what exactly is the value of these projections? Now obviously these projections will be giving the resultant magnitude of the resultant, which is the A vector. Now what can we say about the values of these projections? Now AX, as you can see, this is AY, so obviously this will be AY as well. Now if I observe the triangle, let me name a triangle. We have O, let this be A, let this be suppose M, and this is N. Now in the triangle OAM, what we have is triangle OAM. What we have is AX divided by this is perpendicular, so that's angle AMO. Angle AMO is the right angle, that is 90 degrees over here. Now AMO or OMA, whatever you can take it as the sense, but in that triangle what we have is OA is the hypotenuse, where OM is the base. So the base OM, which has the value of AX, divided by the hypotenuse OA, which has the magnitude of A, is equal to the cosine of the angle, that is cos theta. So in that case AX is equal to A cos theta, while the other way around, that we can see AM, which is also equal to ON, the side, the perpendicular side in the same triangle, or in the other triangle OAN or ONA, whatever you can take it as. But in those sides, in those cases, in those two triangles, you have AM to be equal to ON. So that is why we can take it as the perpendicular in that. So AM being the perpendicular, AM divided by OA. So AM has the value of AY magnitude wise, and the magnitude of OA is obviously the magnitude of the vector A that we have considered, and this has to be equal to the sine of the angle, that is theta over there. So you have the value of AY to be equal to the magnitude of A multiplied with sine theta. Now with these values available, let's check what we have got over here. So AX can be replaced by A mod cosine of theta squared. So this is A squared and this is cos squared theta. And then we have A mod squared sine square theta all under root. And so this, in this case, what we have is A mod squared can be taken as common, and what we have is cosine square theta plus sine square theta all under root. Now A square taken under root is simply A. I'm writing it as A without giving the vector notation because we are just concerned about the magnitude now, and we know that we are just calculating the magnitude. And cosine square plus sine square gives me 1. So cos square theta plus sine square theta is giving me 1. So 1 under root is 1. So what we are getting back is A, which is the magnitude of A that we had predicted. So here what we have done is we have resolved A to the perpendicular or the rectangular components in a coordinate system. Now this is just the two-dimensional case. We will be extending it to three-dimensional case, but before that, let us consider the addition of vectors by rectangular components, and let's see if it's giving us the same result. Now if I have two vectors, suppose, let us take them as A and B. We have the A vector like this, and just to simplify the case, we have a B vector which is going this way, and from the look of it we have the resultant which can be obtained by triangle law of vector addition, which is the third closing side of the triangle taken in the opposite sense. So we have R over here, which is the resultant of the addition of A and B vectors. Now we put this whole thing in a coordinate system, a two-dimensional coordinate system. So that's more or less the two perpendicular axes, that is that is the x and the y axis. Now if we are to consider the components of A and B along those axes that we have just drawn, we can just drop perpendicular from each point of those vectors. That is, I drop a perpendicular on the x-axis from the initial point of A, and then from the ending point of A. So this is more or less the projection of A on the x-axis. So this is AX. Then as you can see, the initiating point of A is just the ending point of B. Let me redraw it because it's not to the point. Okay, now it's on the point. So this is more or less AX, which is the projection of A on the x-axis. Now, for the projection of B on the x-axis, we again drop the perpendicular from the ending point of B on the x-axis, and so this simply gives me BX. And as you can see, you can just observe that this is nothing, this whole thing is giving me the component of R along the x direction, because as we have gone from one point to other, that is from the initiating point of A to the final point of A, then from which is also the initiating point of B to the final point of B or ending point of B, we have got Rx, that is the total projection of the R vector on the x-axis. Now, going back to the y-axis, or the projection of A on the y-axis, we are taking it over here. Then we take it over here, that is this is giving me a y projection of A vector on the y-axis. Again, here we have the projection of B on the y-axis, and as you can see, this entire thing is giving me the projection of R on the y-axis. So what this actually suggests is that you have Rx, which is equal to the projection of A and projection of B on the x-axis, and then you have Ry, that is the projection of the resultant, as the projection of A as well as the addition of the added to the projection of B along the y-axis. So this is how we are obtaining the vector addition by rectangular components. And so we have R to be equal to the resultant. As we know from the previous case, we have R to be equal to Rx squared plus Ry squared taken under root. What this also means is that we can represent the R vector as AX I cap plus BX I cap plus AY j cap plus BY j cap, right? Which is bringing us back to the original form where we have AX I cap plus AY j cap plus BX I cap plus BY j cap. And this is nothing but the A vector with the two components available. And this, obviously, the second term is the B vector with its components intact, and this resultant, as we had taken, is the addition of A and B vectors. So we can go the other way around as well, which will bring us to the same conclusion. The other way around is not just like this, but the complete setup over here. We will be obtaining the same case where the resultant is simply so what is this Rx term we have obtained over here, and Ry term we have obtained over here, and so we have from this we can say, we can also have that, let me write it over here, R equals to Rxi cap plus Ryj cap. And from that we obtain this, and we can just relate each and every term that we have considered over here. So that's more or less the vector addition by component method. Which is a much easier way to consider the vector addition. Now, as I had said, we can extend this vector resolution into three-dimensional case. So, the rectangular components in three dimension. In case of three-dimensional space or three-dimensional coordinates, what we have is we have a y-axis over there, an x-axis in this along this direction, and we are drawing 3D on 2D, so this is how we represent it, a z direction over here. Right. Now we have a vector A over here, and we first of all, now this is extending to the extending out of the plane of xy. You have to imagine it outside the plane. You can just consider a stick which is projected from the corner of your room where you're sitting and watching this video. So from a corner of the room, a stick is just projecting outward, and in that case we have its projection, one of the projections, to be falling right on the floor of your house like this. So this is the floor of your house, and you can just extend its component. The shadow, you can say, is given like this. This is more or less the shadow of the stick that is projecting out. Right. So then we can consider the projections on the walls as well. So YZ plane is one wall, while XY is another wall. Okay, while XZ is the floor of your house, of your room, and the stick is projecting out, and that is the vector A. So the projection of A on the XY plane may be something like this. And then on the YZ plane extends like this. Okay. Now what we do is we like construct a parallelepiped out of it, which will give you a three-dimensional view of exactly what I'm saying. I'm trying my best to give the three-dimensional view of this particular thing to you, so it'll take a bit of time. Please cooperate. That's more or less a parallelepiped. Now this, the rounded off thing, is the actual vector whose components are on the x, y and z direction. So you can just consider a box where you are connecting a stick long enough from one corner diagonal, the top corner diagonal, to the bottom corner. So this complete diagonal is the vector, just like in the case of a parallelogram or in case of rectangle that we had considered for the rectangular components in the previous case, which was obviously the diagonal in that case. And here also you have a full parallelepiped, that is a rectangular shaped room, where you are considering the vector from the top corner to the exactly opposite bottom corner, the complete diagonal of a parallelepiped, and that is the given vector, while the dimensions of the room are the components, are the rectangular components in that case. So as you can see, we have the projections of, this is AY, that is the projection of A along the y-axis. This one over here is AX, as well as this one too. This is also AX. These two being AX, and finally you have this is also AY, as you can see, because these two lengths are the same, while you have another component in excess, that is AZ, that is this one. Let me use another ink for it to show you the AZ part. This is AZ. So this is AZ. So now you have all the three components of all the rectangular components of A in three-dimensional space, where you have a vector A to be equal to AX, which is along the x direction, so AX I cap, plus AY J cap, which is along the y direction, and finally AZ K cap, which is along the z direction. So these are the rectangular components in three dimension for a given vector. As is the case with the two dimension, we have the modulus of A to be equal to AX squared plus AY squared plus AZ squared, all under root, and the cosine obviously goes to 90 degrees, so that does not exist. Now with this thing available over here, what we can say is that we also have a few other terms to consider. Now let us suppose that this A vector that we had considered, I'm drawing this once again to give you a better view of it. We have the x-axis, the y-axis, and the z-axis. We have the A vector over here, and the A vector is supposedly making an angle alpha with respect to x-axis, beta with respect to the y-axis, while it is making an angle gamma with respect to the z-axis. So in that case, from the triangles that we can consider, we have cos alpha to be equal to ax by a. Obviously, this one was obtained right in the previous case where we had considered the two components, or the two dimensional case. But for the other term, we had considered sine of the angle. Here we are considering the cosine of another angle, that is the uh, angle beta. Obviously, you have alpha plus beta in this case to be uh, not equal to 90 degree, because this is a three-dimensional case. So we need not consider that to be 90 degrees, that is alpha plus beta. But here we have cos beta to be equal to ay divided by a, and cos gamma to be equal to az divided by a. So with all this information available, we get back to the same thing, but we also draw a conclusion that ax is equal to a cos alpha, ay is equal to a cos beta, while az is equal to a cos gamma. And just taking the square of all these terms, we have ax squared, and adding them up, ax squared, ay squared plus az squared, all get added to give us a. But in this case, we are getting a square cos square alpha plus a square cos square beta plus a square cos square gamma. But as you know, from this formula over there, over here, that I have just rounded off, that this a square ax square plus ay square plus az square will simply be equal to a square. So this being equal to a square, all the a squared on both sides can get cancelled. I'm writing it over here at the top. We have, I'm writing it over here. So we have a squared to be taken common, and all that we have left is cos square alpha plus cos square beta plus cos square gamma equals to a square. The a squares get cancelled out. All we have left is 1 over this side. So we have cos square alpha plus cos square beta plus cos square gamma to be equal to 1. So these cosine terms, the square of the cosines is giving us 1, and these cosine terms whose square give us 1 are popularly called as the direction cosines. So these very terms that I am rounding off right now are known as direction cosines, because the squares when added give us the value 1. Okay, so that's it about components of vectors and their additions in this video. In the next video, probably we are going to start off with the multiplication of vectors, and then we are going to further proceed to the other rest of the part of this chapter, the properties of vector multiplication, just like we had studied about the properties of vector addition, the unit vectors that are involved, and many more things. Till then, thank you.